Hello everyone, good morning. I'm Genet. I'm a postdoctoral researcher at FITS Karlsruhe. I work with knowledge graph embeddings and also larger language model. It's like, the intersection of knowledge graph and larger language model. So first I want to say thank you to Ricardo and also NFDA for data science for creating this opportunity for us to share our experiences with each other. So saying that this would be a very, let's say, very basic talk, like fundamental introduction to knowledge graph and larger language model. When you see the tutorial, you can already understand that there's a lot more that could be done with it, right? This is like an intro to someone who has no idea about what a knowledge graph is, let's say. So what I would cover is first we discuss a bit about knowledge graph, and then knowledge graph embeddings, that's representation learning on knowledge graph. And then I will proceed to larger language models. But you can hear me, right? It's a morning voice, so I'll try to be as loud as possible. So, knowledge graph. What is knowledge graph? In a way, like the term knowledge graph was first coined by Google, right? Before that, the concept was there, but the term knowledge graph became a thing after it was coined by Google. So if you have noticed, we all use Google like on our daily lives, right? So whenever you search for something on Google, you will find, for example, this you see here, I just Googled NVIDIA. And then you can see on the right side, this one, which is the box which contains this structured information, what they called knowledge panel. In this knowledge panel, what you have is a structured information about whatever it is that you Googled for. In this case, NVIDIA, right? So on the left side, what you see earlier, previous slide, it's probably like from the first article down, it's a list of documents, what's retrieved. On the right side, you have a structured information. So where this is coming from, it's coming from the Google Knowledge Graph. So the source to create the Google Knowledge Graph could be anything else. Mainly it's Wikipedia, right? But the information that's displayed here nicely is actually coming from their knowledge graph. So you see here there are things like there is text, right? There is entity. Like you see there, CEO Jensen Hong. This is an entity, a person, right? And then at the bottom you see something like founded April 5, 1993, which is a date. And then you can go down and see these profiles, and also people also searched for it. You can imagine what is behind this, so you can see, even if you don't want to read the rest of the result, you can just look at this structured information and go with it, right? Move on to your next thing. This is the same thing as what you see on Wikipedia. When you look at Wikipedia, there is info box on the right side, right? So just like that, we have this on Google. So what's a knowledge graph? What it does, it describes real-world entities and their interrelations, which is organized in a graph form. And it defines also possible classes. Classes, we will talk later a bit more, but classes which are like a group of entities or individuals that have things in common. And then the relations between these entities, which is represented in a schema. And then it allows for potentially, arbitrarily, like interrelationship between these entities to be represented. And you can use knowledge graph nowadays for, I can say, any domain, right? Pick the domain and then you can create a knowledge graph for it. So that's interesting that it's that much applicable. So for example, what's a knowledge? How can I actually represent it? So there is this sentence. It says NFDI for data science has spokesperson Sonia. Somebody gives me this, and the first thing I notice is NFDI for data science is a subject, right? And then has spokesperson, I can take it as a predicate, and then Sonia as an object. Now, if I want to visualize, okay, how can I actually represent this in a graph form? I can go and create these nodes, the nodes representing the subject and the object, right? So for the subject, I have NFDI for data science, whatever that's in circle is the node in the graph. And then I have has spokesperson, and then I have the subject for the object. For the object, I have Sonia there. And then I can see I have has spokesperson, which is the verb that I have, the verb phrase that I have in the sentence, which actually relates the subject to the object. And then I can put it as has spoken. And then you can see there is a direction, right? In the text itself, there is a direction coming from NFDA for data science to Sonia. Now, in the graph also, I expect the same thing, which has to be a directed arrow. Altogether, it makes it a directed, edge-labeled graph, right? Just for this particular sentence. Now, we can put this as we can give it as a formal definition for it, right? So, the first definition that we see here, a directed, edge-labeled graph, G, which consists of V, which are the nodes, or what we say usually in graphs, vertices, which have a size n. So, you can consider this as entities, which is a usual term in knowledge graph, right? What we say here, nodes or vertices, what you usually call when we work with knowledge graph embeddings, what we call entities in our graph. And then we have a set L of edge labels, the labels, like for example, has spoken, has a spokesperson from previous example, which is a set of labels we have. Now, a set E of directed edges, E, which is a subset of V cross L cross P. This is, in simple terms, the triples that we have in the knowledge graph. So we can define this formally like this. And now, what I have already mentioned, entities and relations. The entities being a thing of distinct and independent existence, something which has to be distinct, and it should have an independent existence for it to be called as an entity. And then we have the relations, which describes the interrelationship between, or the relation, whatever relation between a node and another node. Now, what else can I actually represent? We can have more and more information, right? Now, let's say, now I want to add one more sentence to it, which is an FDI for data science was established on, this is a random date, okay, because I do not know when it was first established because I joined a bit later to the project. So I just gave it a random date. I want to say this first. So I just put there for this particular example, 1st February 2020. So now I want to add this to the knowledge graph. So when I add it, what I do is, as a subject, I already have in the knowledge graph, which is an FDI for data science node, right? Now I want to connect it to the information, which is a date. And dates are considered as literals. So literals are things which describe data values that do not have a separate existence. This is argumentative, but whether in a knowledge graph you have literals, these literals are always associated with some entity because they always appear in the object side, if you have noticed, if you're familiar with it. So they never appear as a subject, those literals. So now this date is a special kind of vertex or node in a graph, which is associated with some particular entity. So what I do is I just put one edge between this subject node and the date that I have. And then what's my possible property established on, right? Which I will add as a label to the edge, to the outgoing edge from NFDA for data science to this date literal value. Well, when you talk about literals, literals can be text, right? Literals, short text, for example. I can say NFDA for data science, even the node itself can be further labeled as NFDI for data science, not the letter for, not the acronym, but the whole text. This could be given as a literal value to the node. And I can have a long literal value, long description. Let's say 1 or 2 sentences describing NFDA for data science entity. That by itself is a literal value. And then I can have numerical values as literals. For example, if I'm interested in, let's say, the number of members of NFDA for data science, then this will be a number value, right? Numeric value. Then if I'm interested in the height, age of Sonia, then I will have that as numeric value, which are literals. What else can I put there?
Stock price, maybe?
Sorry?
Stock price, like price of a stock.
Yeah, exactly. So those are numbers that could be represented with literals. So another thing that you can think of already is to add to this knowledge graph, small graph, is what's the type of these nodes, right? So I have NFDI for data science. What is it? It's a consortium. Now I want to add this sentence, NFDI for data science is a consortium, to the graph. So what I do is create again another node, which is named as consortium, and then I create a connection. But notice the difference between this node and that node over there. This node is an individual, which is an individual or a member of the class, which is consortium. NFDI for data science is one consortium. There is NFDI for chem. There is an NFDI for math, right? Other projects. So all together could be considered as a class, which is consortium. That's what we have a definition there. So classes, collection of individuals or objects defined as either extension or intension. Extension means, for instance, better with an example, all the attendees of this summer school. I can just name everyone, right? Then I can put all together and create a class. That is what an extension is, because I have the members already fixed, I know them. And then there is intention. I can define some kind of axiom to create the class itself. With some rule, this is my class. For example, this is a consortium, is an intention class. So let's just look at one example together to see what we can do with knowledge graph. I hope it's visible to you. Is it? Hmm? No. Okay, let me try one thing. Better? Okay. Yes, introduction to knowledge graph. So what we will do with this one is we try to use this library called rdeflib. Those of you who are already familiar with knowledge graph know the library for sure. So this library is a Python package which you can use to work with rdef data that you have. What it can do is you can parse and also manipulate your data with the library. It has a parser, it's serializable. So these serializers, I didn't go in detail again. These serializers are different formats to represent your data. So there are rdef XML, N3, N3+, N quads, turtle, which is very, very common, right? So we will see one example with that a bit later, okay? And then you can create a graph interface, you can have store implementations, and also you can query it using Sparkle through the library. Now let's create a graph. So first we need to install. I'm not going to run it here because I already ran it, so we just look at the results, okay? To save time because, well, we had to. So now we install the libraries that we need, rdeflib, py.plus, graphit, so we can visualize the graph. So once we have all the libraries we need imported, what we do is, you see here, ggraph. Now I'm trying to define a turtle data, one of the serializations we saw earlier, right? So this turtle serialization is, I want to show you a different data, not this one moment. We have the same example with NFDI, that would be great. One moment. So it's nice to look at with the same example with NFDI. It's better than a movie. This one is about a movie, which I'm sure you are familiar with, a very common data, but let me see if it is, hopefully, it's the same one. Anyway, we can look at it, it's fine. I've changed it, completely fine, I have it here as well. So this graph here, this is a fraction of the knowledge graph that we have created for NFDI for data science. We have this ontology, NFDI for data science ontology, and based on this ontology, we have NFDI for data science knowledge graph as well. So I took part of it to show it to you for this particular example. So you see here, I have the tetra format. What you do is you take the subject entity, and then next you put property value with a semicolon separating it. Property value, property value, property value. And then when you are done with all the property value pairs that you have for this particular subject, you put a full stop here. Point, and then you go to the next one. So it's a very simple serialization turtle format. So I have here NFDI for data science type consortium. NFDI for data science, I have all, I think it's all of the COSPOX% that we have for NFDI for data science. We have them here listed. You see there, probably you also see Ricardo there. So now I have NFDI for data science task areas that are defined in NFDI for data science. Task area TA1, task area TA2, there are 5 of them, but I put 4 here just to make the example not too big. And then it's type task area. So what you see here is task area TA1 is an individual, right? An entity. And then I have task area there as a class, that these task areas belong to this class. And I have one more task area, TA1 has lead NFDI for data science fits, and also as a person has a lead Harald Sack. So given this knowledge graph, what we can do is we can just print it just to see slightly differently. For each subject, predicate, object, just give me all of them printed. So you see here maybe slightly better because of the colors, I don't know, right? So I have the subjects, I have the properties, I have the values here. Now, I want to change the serialization from turtle to arraydef XML. What I need to do is just g.serialization and give the format you want to change it to. And then you have it here. This one, arraydef description about, you put the subject there, and if they're for data science, and then whatever properties and values you have, you put it like this. And then you close with arraydef description and you continue with the next subject property value pairs. So this is another serialization you can do. If we want to add more triples to it, let's say I want to add the label of the node that I have task area 2, which is research knowledge graphs. That's the label of the task area. And now I want to add it, then all I need to do is define a literal, and then I will create a namespace because I need it, right, for the subject. Then I have the namespace for the subject task area to please add arraydef label, this label I gave you. And then now let's visualize it again to see if the change we made is there. Do you see the third one? I don't know if you see the cursor. Do you see this line? I hope at the back, I don't know. So you see there, it's added. Now we have the label, right? So now what we want to do is save the graph, NFDI for data science KG, which is saved somewhere. And now I want to visualize it. So to visualize, I can use this KG lab. All I need to do is load this arraydef to KG lab, and then I can do also some statistics to see how many entities I have there, how many relations I have there, a little bit of manipulation. Then, sorry, it tells me there are 29 edges triples, right? And then I have also this much, 29 number of nodes in this graph. Then all I want to do is visualize it. Now to visualize, I can say the color if I want to differentiate. In this example, all the prefixes for the instances and also class are the same, so it wouldn't matter But what I did here is for each prefix, I gave a different color so you can see it on the graph. So I have it open somewhere. So do you see it? Again, because this laptop is not so friendly right now. Okay. So this visualization is a little bit, it's not static, you can move things around. Now I want to move it around to see, whatever in bold is the edges that are connected to the node that I'm literally holding right now, which is this one, NFDA for data science. So you can do this visualization when you have a rather small knowledge graph to see. For you also to be interesting to see, is it a very dense graph you have, is it connected, is it like sparse, wherever, then you can just look at it like that. Now let's go back to our collab. Where were we? We're here, right? Now another way to visualize is you can also visualize it right here with PNG. Do you see? This one is static, so it's not so pretty, but you can just do it directly here in Colab. So it just shows when you got it down, you have NFDA for data science, and I have all the other objects that this node is connected to here. And then if you see, it puts also the label there for NFDA for data, what I have added. So let me proceed to save time. Now I want to query, print all cost box percents of NFDA for data science from this graph. What I do is for cost box percent in this object, please print cost. You see here, I give the predicates, the subject, and I have all the cost box percents printed like this. So I have this Adam down to Soren to Zavash, whatever that we have in the knowledge graph, which is printed. Another way is to query it with Sparkle. So I couldn't go with time to talk about how we can use Sparkle, but hoping that you are familiar with it. So this is a very basic example for Sparkle because the question is very simple, right? It's not a complicated question. So you just you put the prefix that you need. For us, it's NFDA for data science. NFDA for DSO is the prefix. And then all I do is, as a subject, I have NFDA for data science. And then as a predicate, I have cost box percent. And please give me all the objects that you have there. And then when I print it row by row, this is what I get, the same result, but using Sparkle. So I guess that's all for this part. You can play with it yourselves if you are interested to know a bit more. Now let's go back to this. So, what are the popular knowledge graphs that we have so far? Like few of them that you see here. There is Wikidata, there is DPpedia, there is Freebase. Freebase is no longer maintained, but it was a thing back then when it was created by Google, and still we use it. Like there is Freebase 237. Some of you, I saw knowledge graph embedding posters, so you're familiar with it, I would say. So we use some of the data sets from there, from this knowledge graph, to do some link prediction tasks on it. So these are the openly available knowledge graphs that we can play with. They kind of inspired a lot of people actually to work on knowledge graphs, I would say. So what are the applications or the use of these knowledge graphs? The major use are, they can be used for recommendation task, and then you can use it for language understanding, information retrieval. We saw it for information retrieval with the search engine, right? With the very first example I gave. And then for question answering, it's been used in IBM Watson, Cortana, Siri, and you can think of many where knowledge graph is playing a part. So what are the domains that we know already that it's making a little bit of an impact? It's medical, cybersecurity, financial, news, social networks, scholarly, what this summer school is about, right? So you can find scholarly knowledge graphs like AIKG. So these are interesting application areas for knowledge graphs. What's difficult about knowledge graph? Have less time. So what's difficult about knowledge graph? They're hard to manipulate, right? Because knowledge graph has a huge dimension and it's sparse. Not every node is connected to every other node in your graph, which makes it difficult. And then when you want to apply machine learning algorithms on such kind of data, it's difficult. And mostly for this kind of tools, learning tools, the data that you give are tabular, right? You have features and then you give it in tabular form. And then it's some algorithms, well, the important ones are NP complete if you want to do this on graph. And there is a problem of incompleteness. It's never complete a knowledge graph because of this open world assumption. We cannot say for sure, oh, everything that has to be true about this domain is in my knowledge graph, that's it. There is nothing that will come which will be true. We cannot say this, right? So always it's incomplete and we have to find a way to actually add data there. Another reason, the way it's created. You can create it manually with some experts. You can write a code which extracts, for example, from text different relations and then add it to your knowledge graph. And then you can do it semi-automatically or you can apply heuristic. All this tells you that it's so obvious that your knowledge graph is incomplete, or you cannot say for sure it's complete. So what you can do there is, for this manipulation problem, one possible solution is mapping this high-dimensional graph to low-dimensional vector space and learn embeddings for it, right? And for this incompleteness, one of the tasks that we have been doing so far is link prediction. Predicting the link between the nodes that you have there or new nodes you want to bring into the knowledge graph. So altogether, for link prediction, we have embedding-based link predictions that we will see because there are different kind of link prediction as well. So with that, we go to knowledge graph embedding, right? So what's knowledge graph embedding? Look at this graph. Let's move a little bit out of NFDA for data science and look at a different example. I have this graph here which talks about, I guess, two scientists. It's Tim Berners-Lee and Nigel, their birthplaces, their occupation. So both are founders of Open Data Institute. Then I move this to a vector space that I would expect from this small knowledge graph that Tim Berners-Lee and Nigel will be somehow close together, right? In the vector space, not so far apart because they have things they share in common in the input graph. So this is what we want to achieve when you learn the embeddings. And how it could be done, you have link prediction task, triple classification, or what we call it entity typing you can do to achieve this. And then you have out of KG application of this. You can use the embeddings that you have learned for other tasks, recommendation, question answering. Well, now let's see, for example, what's the occupation of Nigel Shadbolt? What would you say is the occupation, if you have to guess?
Founder?
Exactly. So I have as a occupation because the others, so founder is already there. So as a occupation, I would say it's a computer scientist because the other founder is also a computer scientist. And then I don't have any other data to say, oh, he could also be another, he could also have another profession, right? But based on this, I can only infer that. So now what do I expect from knowledge graph embedding? There are things like symmetry. Symmetry means Mary married to John. John is also married to Mary, right? Both have to be true. And then I have Mary, child of Petros. This is asymmetry in data, you see. It's not the other way around. And then I have inversion, Petros, father of Mary. I would also put it around and say Mary, child of Petros. These are patterns you see in data. And then you have composition. For example, Mary is a child of Petros, Petros sibling of Jack, and there should be a relationship between Mary and Jack with the relationship niece, right? So these are what I would like the embedding model to also capture and understand, right? Now, there are some models which are, these are the basic, let's say, Trans-E is the first, I would say, the one which was kind of a foundation for knowledge graph embedding models. And then after that came distal complex. There are plenty others. If you want to see, you can look at my survey as well on this. And you can look at the symmetry, asymmetry, inversion, composition, which of these embedding models capture which part. So whenever you choose a knowledge graph embedding model, you have to think of what it is that you want it to do for you. Now, Trans-E is the only one I will cover here. So Trans-E is a translation distance-based model. The idea behind this is, so if I have an entity, for example, now I'm going to replace ESRP with a real example. So German, capital, Berlin. Then I have German plus the embedding of German plus the embedding of capital should approximately be equal to the embedding of Berlin. This is the idea of Trans-E. Approximately should be equal. So you see there, ES would be German, RP would be capital, and EO would be Berlin. I mean, these entities' embeddings. So you can already see why it's not able to do symmetric, right? Because if I say German plus capital is equal to Berlin, then I cannot say the other one way around, Berlin plus capital is German. That's not possible. That's why it doesn't capture symmetry. So let's quickly go to notebook, okay? So, okay. We will look at a simple example with Trans-E. So this is using this AmpliGraph. If you're familiar with it, you know the different libraries, right? Pykin, AmpliGraph, and also a couple, a bit more other libraries that you can use. So with AmpliGraph, you can also find a tutorial, this kind of code on their library page also. It's just, we just look at it here, and then you can further dig it there if you're interested. So what we do is install libraries, we train a bit model, we evaluate it, and we see how good or bad it is in predicting. So let me start with, so you have to, this part, I guess you're familiar, so I'll just quickly pass, okay? Then install the libraries you have to mount in case you want to have the file saved. And then let's go down a bit, look at the data. Here I'm using the data that they have also. This Game of Thrones, do you remember Game of Thrones? I'm sure all of you, I could say, highly likely. So this is the Game of Thrones data from this data set that's available publicly. And then we want to see the top 5 triples they have. You see there's Smitten, Serov, House Shermer of Smitten. Sorry if I'm pronouncing it not right. And there is House Mormont of Beer Island, blah, blah. These are the 5 triples that to see, so you can imagine what it looks like in there. And then when you check the number of entities, there are 2,050 entities in there, and the relations are a few. You see there is allied with, branch of, founded by, here to, in region, led by, blah, blah. These are the relations that they have in the graph. Now we want to split data set into train and test. For this example, of course, you know you can do this also like train, validation, and test. Validation is important when you want to do early stopping to avoid overfitting or underfitting, right? So here it's just train and test. Now we want to split it. Either you can split it like 20%, you see, which is commented out here, or you can just do, okay, number of tests, I want only 100 triples to be in my test set, and the rest would be training. And then you have this size, you see here, 3,075 for training, 100 for test. Now I want to train it. What you do is, again, this is something you can easily find there, this part. So I wanted to use Trans-E. So scoring type, you can replace this with distal, with complex, or any other scoring based model you want to see. And then you can compare the results that you get with it. And here you can fix the the dimensionality of the embedding space, if you want 50, 100, 150 to be the vector size of your entity embedding. And now here we can determine the optimizer, the loss, the regularizer you want to use for it, to set it, and then compile the model with that. And fitting is where you actually train it, right? It's trained now. We don't need to look at it, but you can see it is 200 epochs, and then it's trained for 200, and then go down. Positive filters. This part is because we do create negative samples, right? That's whenever you create negative samples, is what you do is take a true triple and then corrupt either the head or the tail, right? Sometimes you can also corrupt the relation actually, but what's common is you corrupt the head or the tail entity. So you can create negative triples. Because you do this randomly, you may end up having true triples as negative triples. And you want to avoid that. That's where this filtering comes. So if you have seen it with knowledge graph embedding evaluation, there is with filtering and without filtering, right? Now we save the model, and then we can delete if we want, and then we can restore it again, and then we check if it is fit. Let's do evaluation. When we evaluate, we want to filter it. We don't want true triples to be considered as negative triples. And then I have the evaluation result here. You can use MR, the usual scoring methods. MR is considered as not so important now. Usually before, we have always used MR as well. MR is this mean rank, the average of all ranks of the triples, where the smaller value is the better. So MRR is the average of the reciprocal ranks of all the triples you have between 0 and 1, and the bigger the value, the better, right? Now in hits at 10, you have, which indicates how many times in average a true triple was ranked in the top ends. Top end, like if I want hits at 1, so how many of those which was ranked the first are correct? That's what it captures. Here you see the MRR is 0.05. It's quite bad, right? It's because it's just an example. Then for you, you can think of how to improve this. Which part what should I do with which component to get a better result? And you want to predict, you can put these unseen triples, and then you tell it to evaluate the model with the unseen triples, and then you can now get the scores for this for these unseen triples to do the prediction. And then I just printed with the data frame. You can see here Dinosaur Targaryen allowed with House of Stark. And then I have for this, the score is, because it's a bad, it's not well trained, right? We saw the score. So it's negative 9.16, that's a score. And everything else which comes after that is even worse because it's a ranked score. But the point is just to see how it works. Well, you can visualize it with TensorBoard, but not on Google Colab. The point is that you can see, even like after converting to 2D, how good it looks or how bad it looks, so it can give you some insight. Well, with that, we go back to, I started a bit late, so I will be given some more minutes, I think. So let's last part of our tutorial, large language model. So there was this stopped. No, it says the host would like you to unmute. Oh, okay. Unmute. Okay, now? Good? Shall I continue? Okay, so there's statistical language models, right? Then I want to go in detail, but if you remember, they were the hype back then. And then comes these early neural language models, and then they were hype. And then we have, it's not exactly this kind of strict timeline that I'm showing here, but it's just the idea, you get it, because some of them could overlap, right? It's not that they did the research on this, ended, and then continued on the other one. And then come this pre-trained large language models, BERT, and then we have these large language models now, ChatGPT, the era of the ChatGPT and these large language models. So these transformer-based pre-training large language models, you can categorize them based on their neural architecture as encoder only, decoder only, or both encoder and decoder. So these encoder only are they're focused on understanding, interpreting text. It's like someone who plans or who wants to read but not write. It's just like for the model. So they read, understand, but not write. And then they are good at these classification tasks, sentiment analysis tasks, which require text understanding. Example, BERT. And decoder only, their purpose is the other way around. Their focus is to write, right? Generate text, like the GPT family. Decoder, encoder, to do both, like translation task. T5 is one example for that. Now, these families, I'm not saying these are the only ones, as you can see with those 3 dots. There are plenty more large language models, but these are the 3 mostly known large language model families. The GPT family from OpenAI, the Llama family from Meta, and the Palm family from Google AI. And these are, like, you can kind of characterize them as, these are large compared to other models because of their neural size, the number of parameters that they have, and they are general purpose trained on different kind of data, which is not specific to a certain domain, and they have the ability to be pre-trained and fine-tuned. Now, applications, they can be used on question answering, content generation, chatbot, which GPT. And then what are the limitations, though, with these large language models? So you can think of hallucination, right? The main, I'm sure if I ask you if I had time to tell me like 1 or 2 examples you remember when ChatGPT came out first that you were writing and getting some funny answers. So remember that time, right? How it hallucinates if you ask it something that it has no idea about. It doesn't tell you, it doesn't know, gives you some very funny answers. That's a hallucination. And the data privacy, so whatever you give to it, it may leak it to someone else, right? And then there is bias. It's biased like any other model on what it's trained on. This plagiarism, you can use it, ChatGPT, create a text and give it as an assignment. And then it doesn't tell you from which resource it got. Now there are works, of course. Now GPT-4 also tells you citation, right? It's coming from this and there. And then updates take long to actually train them. It's difficult if you want to, because there is a timeline from this up to this. If you remember ChatGPT, it used to tell you like it was up to this time that it was trained on. So sorry, I don't have information to answer your question, something like that. Now, if you have to retrain it, it's very expensive with the new thing. Limited domain specific data. So since it's generic, if you come up with some specific domain to use it, then it wouldn't work, right? And then outdated data, which in a way is what I mentioned already. It's maybe data from back then. Now every 5 months or less, new things come up and falsifies whatever was true before, right? So to that comes this retrieval augmented generation, one of the approach to deal with some of the problems we have just discussed. I'll give you an example. What are the I'm asking this to a large language model. So I did this with GPT 3.5, if I recall correctly. So what are the affiliations of Professor Dr. Engineer Stefan Wolfinghoff? Sorry. And then the answer was, I'm unable to provide real-time information on individuals, blah, blah, blah. So I would, as a user, like to get a better answer than that, right? So now what we can do is let it use external resource where there is information about this professor, right? And then from that resource, create or extract context that would help answer the question, and based on that context, give me an output. The above part is real, the bottom is made up, okay? Just it's not like some trained model that I tried on, but the idea is because this information was available already on the website of this professor, so if we use that website, this should be the answer that we get, right? So I have this professor, Dr. Engineer Stefan Wolfinghoff, is a professor of computational material science. Now, computational material science, maybe, if I can say, is a specific domain, like mainly when you have to talk about people, then it lacks information. But if you help it, giving some context to it, it should be able to answer like this. Now, let's go to notebook, okay? Okay. My cursor is gone. Now let's see some examples with RAG. That idea of how we can actually use it. So installing the necessary libraries, and then loading the model and the tokenizer, pass this along. And then here I just, because when you use from Hugging Face a model, you need to use it token for easy authentication. It's just that part. And then I'm using Mistral here, because Mistral 7B, it's an open resource model, right? So that's, well, because a lot of people use it for this particular reason, because it's open source, you have a lot of results there which you can compare your approach against. So one of the reasons for using it. The other is, when compared to the other open source LLMs, this one does a better job on most of the tasks, also if you have seen the paper. That's the reason it's selected. Anyway, you have the model, Mistral, which is version 3. And then what we do is we load the model, and then we do a bit of testing with the question we had earlier. This time it's not co-spokesperson, it's spokesperson with NFDI dataset I want you to see. So who is the spokesperson of NFDI for Data Science Consortium? I want to know if Mistral knows this already. Now I run this, look at the output. I'm not running it here, obviously, time, it's already run. So the NFDI for Data Science Consortium is represented by the question is who is, right? So by the NFDI for Data Science Consortium spokesperson, the NFDI for Data Science Consortium spokesperson is elected by the NFDI Consortium Assembly. So it's about the consortium in the process. So there is nowhere, at least, and I have tried with up to 150 or 200 token size to see the result, okay? Now it's 75, but I tried a bit more. So it tells you how the spokesperson, whoever that is elected here, without actually telling you who it is. So what can we do with that? We have to give it some info so it can actually tell us, right? So I will tell you the idea for this. There is a paper we have presented at KDD in one workshop, which is this part I took from the paper, but part of it, not the entire component. I removed some for simplicity, okay? So here, extract entities from the question text. I have the question text, I get the entity, and then I go to the knowledge graph and map it to whatever entities I have in the knowledge graph to find which entity is being talked about in the question. And then from that knowledge graph, I'm explaining it now so I can go quickly. Now from the knowledge graph, from that node, I get the subgraphs, which are important because I have to limit my context, right? Then from that subgraph, what I do is, from the subgraph, I do verbalization to get a proper text out of it. Then that's what I give as a context. So the first step is extract entities from the question text. Let's go down. So we extract named entities. So I used here, where is my cursor? I used this SPACY, the model, this one, the large one, in Core Web LG model. And then I gave this question, who is the spokesperson of NFDI for Data Science Consortium? And the model gave me, as a named entity, NFDI for Data Science Consortium. Now I take this, and then what I do next is I will look at the entities just to show you from the knowledge graph that we saw earlier. Here you see I want to look at the entities and their labels. The first one you see here are the entities, and this is the labels, and these are the relation and the labels that I have. Okay, now I want to match, kind of create, to get this ranked list of entities from the knowledge graph which match with NFDI for data science. Now I'll go down. I can't go through the code, okay? But the point is that you get the idea. So what we do here is loading the model. Then I'm using two different ways to get embeddings. I'm using BERT here. BERT embedding with, you get the CLS tokens as an embedding for the text, right? So I did that. And then also you can just get the last hidden state and take the mean. And that's another way to get the embedding. So two approaches, I'll show you the result later. Now I compute BERT embeddings for the entity labels. Now I have the entity label also. Then I need to get the embedding for this entity label. Now I got the embeddings, compute BERT embeddings for named entities. The named entity, it's BERT embedding, and the entities in the graph, and it's BERT embedding. Then what do? Cosine similarity, and then rank it to see which one best fits, right? Let's go down. So extract subgraph, which I already told you, based on so do you see here, named entity NFDI for data science consortium is most similar to entity NFDI for data science from the knowledge graph. That's a proper exact match, exactly what I wanted to get. So extract subgraphs. From here, I extract the subgraph from this NFDI for data science. A box is, you remember A box, T box? Time?
No, I want to ask a question.
Okay. We can do it later too, or we can do it now. Sorry, I will come with you during the tea time, okay? And then I have this triples in my A box, like entities with another entities connected. And then if I want to see how they look like, do you see this? These are the knowledge graph somehow that I have there. It's bigger than what you saw earlier. Now what I want to do is take only those triples which contain the extracted most similar entity as a subject or as an object. This means one hop, right? One hop from NFDI for data science entity, outgoing edge or incoming edge. I just collect that first. So what I did is the result. You see, the subject is NFDI for data science only because it doesn't appear in this data as an object, I guess, if I recall. So we have this first step, the subgraph. And then I want to verbalize it because if I give this as it is to the large language model, it's just like kind of introducing noise. So now when I verbalize it, one step to do that is replace each of the entities with their labels, removing the IRI part. So I have NFDI for data science consortium, type consortium, blah, blah, that you see here. Now, if you look at it, this also is not there yet, right? It's not a proper sentence. Now, if you want to put this together and create a sentence out of it, a set of sentences, if you read it, it's not very coherent with respect to English language. So I want to see a better way of verbalizing it. So what I did here, it's not just to have the idea of it. It's not, I would say, you don't obviously do it that way, but what I did is I just copied this and I gave it to ChatGPT. Give me a coherent sentence for this set of sentences. Now you see the difference. This is from ChatGPT. For the first one, which says NFDI for data science type consortium, it says the NFDI for data science consortium part. Okay, this is another example. It's somewhere there. It says it's categorized as NFDI for data science, categorized as a consortium. So this is a proper sentence made by ChatGPT for this. Now I'm using this. If I give this as it is, as a context, again, it's too much, right? There's a token limit too. I should think of further reducing this context. What I did is I did a similarity computation between the question text and all this sentence. So when I compute this, what I did is compute similarity between the question text and the list of sentence. Now here, as you can see, I used the get BERT embedding, which is a CLS one with the token. And then it gave me this, it ranked the sentences based on how similar it is to the question text. You see here, what I'm interested in the triple, which says, if I want to know if you are with me, which triple are we interested in from the knowledge graph for this question?
What
Exactly. So I just want to know that the triple which has an if therefore data science spokesperson Sonia. That's what I want to have in the context, right? Now, if you see, let me scroll down. It's down there, number 28. Sonia Schindler is a spokesperson for an if therefore. Now I want this to go up so I can use it for my context. So what I did next is I tried the other BERT embedding approach, and then with that, it kind of moved from 28 to 21, right? Now again, I'm not there yet. I need a better approach. So I wrote of why don't I use SBERT? No, SBERT, sentence BERT. It's better in coding sentences than BERT, right? Sentence BERT. Now let's go down. You see Sonia is now number 5. So this tells you also what kind of embedding method you should use for your task. So sentence BERT does well as compared to BERT in this case. Now, okay, I can use this. Just saying, let's take top 5 up until Sonia. So I used her name a lot for this example, but okay, so top 5 sentences that I put here as context for the large language model. The result is not there, but I will tell you this. If you have seen the top, some of the sentences here, they are not necessary at all, right? It's coming from RDFS label, because the label is already there, and I'm giving it RDFS label. This, you can just remove it from somewhere in the step. And also, there is categorized as this is type information. You can also remove type information, so your context could be smaller. So what I did is removed those things. Then I used only 3 sentences, and I just copied the context here, you can see. So here, as you can see, the context became the NFDA for Data Science Consortium participates in consortium leading. This probably you won't know what is consortium leading, just leave it. It's coming from the knowledge graph, okay? And then Thomas Newmuth is a co-spokesperson for the NFDA for Data Science Consortium, one of the things in the context. Then I have Sonia Schindler is a spokesperson for NFDA for Data Science Consortium. Now this is my context. I'm telling it to use this. Who is the spokesperson of NFDA Consortium? I'm asking it now. I told it to use this context, and I'm saying without adding any additional information. And then look at my result. Let's go down. Who is the spokesperson of NFDA for Data Science Consortium? The answer is it gives me both. There is more work to do. It gives you extra information, but it's right there. It says Sonia Schindler is the spokesperson of the NFDA. This is what we want to achieve with RAG. So make it answer questions that we cannot do otherwise unless we use external knowledge source. That's how knowledge graph could help. With that, I will go back to, I'm almost done. Well, with LLM, there is a lot more left, you could imagine, right? Even with the prompting, you can do a lot more to make it better, to give you just that answer, to kind of restrict it, and you can use chain of thought to kind of create rather appealing answers to your questions. Now, with that, I end it here with some shameful advertisement. I have a workshop on calling with some colleagues, and if you have work on knowledge graph and generative AI, think of submitting there. With that, thank you sorry for using extra minutes. So if you want to talk to me about any of this, I will be here.
Perfect. We're perfectly in time, obviously.
Amazing.
Yeah, thank you. I think we have time for 1 or 2 short questions. Janet, you're going to be around anyway for post
I'm here till
and
5.
I think this is a generous scheme today, so the rest of the speakers advertise your workshops. Questions, Janet? Brian, you had one?
Yeah. So thanks for the talk. I wanted to ask you, do you see knowledge graph embeddings and LLMs somehow being mixed? Can they cooperate with each other in getting better answers?
That's what we were trying so far in our team also to kind of look into. Yes, usually it is, so far it has been easier to kind of give it a text like information as it is without the embedding to the large language model, like the way we talked, right? Now, when we want to use embeddings, it could help, definitely, I would say. Why? Because knowledge graph could be also very big, right? This is maybe a small knowledge graph, but if you think of a knowledge graph with millions and billions of triples, if I'm right, Wikidata has more than 1 billion triples, right? Now, if I want to get more context, for example, from Wikidata, it would be tough because it would limit me. But if there is rather better representations, embeddings for the entities, and then if I can use that to combine it with large language model, I think that would be better.
But it's difficult, right?
Difficult. That's why I don't know if there is a really good work, so no, it's definitely very difficult. Yeah.
A second short question. Yes.
It's kind of specific. I was curious. I didn't understand how the Spacey library is used to narrow down what's the role of narrowing down the triples?
The Spacey was used to generate the named entity from the text, so from the question text. That's the role for Spacey, just getting the named entities. Because, well, I can skip named entities, and I can directly just take that. Another way would be, I don't want Spacey. I just take the question text as it is, and then compare with whatever text I have in the knowledge graph directly with BERT. I can do that, but I applied Spacey there because now the entities that I want to take from the knowledge graph side have short labels. And then if I use the entire question text, it may or may not help. But if I reduce, because it may give me some noise. But if I kind of make it shorter with named entities, then it will be easier to kind of compare later. So I used Spacey to get the named entity. Nothing, it doesn't have any other role.
So it's basically it's drawing from the knowledge graph, like it's searching on the knowledge graph.
No, it's just from the question text. I give the text and I say, please give me named entity. Because if there are more named entities in there, it will also just tell me, oh, this is a named entity. Actually, it would say, this is NFDA for data science, and it's an organization. So it kind of gives you the named entity with its type, if I say so. So
Not
that's
link to a knowledge graph.
no, nothing to do with the knowledge graph. It just stays there at the question part.
Thank you.
So if you have more questions, Janet's going to be around. I'll open the coffee bar now, and we will resume like 11:05, if that's fine for everybody. Okay, then let's thank the speaker again and grab some coffee.